So what I'm doing is I'm starting to wire up the 74HC595, which I've got just here, and the 6 LEDs. And I've gone back to the original configuration with the single inline resistor package here. So I can just go from power, which is powering the IC, and ground on the IC there. Then I'm going to take wires out of the output lines of the IC to each of these 6 LEDs. And then they'll ground themselves through this wire here, through the resistor package. So if we take a look at the data sheet for the 74HC595, it's reasonably straightforward. You've got, obviously you've got power and ground, and then you've got 8 outputs, which they've called QA, B, C, D, E, F, G, and H. I think for simplicity I'll just use 6 off this side and not worry too much about A and B. And then you've got serial data that you put in, you've got an output enable pin you've got to keep low, you have got, well, you've got serial clock, you've got some other pins here. Let's have a look at exactly what they mean. So this is not actually the clearest thing. So what I've done is I've looked into it in a little bit more detail and come up with this diagram to explain how the 74HC595 shift register works. So I think of it now in terms of 3 sections. You've got at the bottom here a shift register, it's the serial in parallel out shift register. Then you've got another register, sort of a secret register, the parallel register, and lastly you've got an output buffer. So the only thing you see to the outside world are these output pins here, parallel out, and the serial in here, and then some other actions that you can perform. A shifting in action, which shifts the data in, a latching action, which moves the data in the shift register into the parallel register. You can do an output enable, and you can do a clear. Now, confusingly, I think in the data sheet, it names these in slightly funny ways. So the parallel out are these ones Q, A, B, C, D, E, F, G, H. You've obviously got your ground and your power. Then OE is the output enable, which controls whether the outputs do anything or go into high impedance state. So they'll either be noughts and ones or there'll be a high impedance state. Then you've got, you can ignore this QH dash for now. This is the clear, which clears the serial register. And then you've got a clock and an R clock. The SER is the serial data in. So the confusing ones are this R clock and serial clock. And I think clock is slightly the wrong term, and I think it would have been better if they had called these actions, not clocks, because they've got nothing to do with clocking at all. They don't really follow a regular clock pulse in any way. You just put in a piece of data, say a 0 on the serial data in, and then you take the shift action from low to high, so from 0 to 1 or 0 volts to 5 volts, and that shifts in one piece of data into the shift register. Then you can put another piece of data here, a 1 or a 0, whatever you want, and shift it in with a shift action. So normally you put 8 pieces of data in turn and shift each one in to fill up the shift register. This is an 8-bit shift register, and you would then, once you've got your data into your 8-bit shift register, you then perform a latch action to copy the 8 bits of the shift register into the 8 bits of the parallel register. But even then, you'd see nothing on the output pins unless you do an output enable. You have to take output enable low in order to turn on this output buffer. But in the circuit I'm doing, I think we can ignore this output buffer completely because I have an output enable permanently tied to ground. So the output enable buffer is basically doing nothing, just passing the data straight through. So the reason why there's two clock pulses is one to shift data into the 8-bit shift register and one to latch the data from the 8-bit shift register into the parallel register. So you can quite happily shift data into the shift register as many times as you want, and it won't make any difference at all until you latch it into the parallel register. And once some data is latched into the parallel register, it doesn't matter how much you shift the shift register, the parallel register will keep the same 8 bits of data latched into it. Okay, so what I've done is I've connected up my, well, you can't really see it, can you? I've connected up my 74HC595 and I've hidden it behind this 6-way cable. And the reason is I'm taking the 6 LED outputs from 6 pins of the IC, looping them through this cable, and here they are along here. And I've then brought in the 3 wires from the Arduino, which are these 3 wires here, pins 8, 9 and 10 of the Arduino, and I've put those into pins that are called, 8 goes into the serial input, 9 goes into the one that's in my data sheet is called the R clock, and pin 10 goes into the SR clock. I found a sketch on the Arduino site that shifts data out. It's called the Hello World 595 shift register sketch, and all it does is puts the numbers from 0 to 255 out, shifted out through the shift register. So let's send that through to the Arduino right now. We won't see all of the numbers from 0 to 255 because we've only got 6 LEDs. There's the familiar pattern of binary counting with the least significant bit on the left rather than the right where you normally expect to see it. But yeah, that's definitely counting. It's nearly getting through now. A little bit more and we'll be at as much as we can display on 6 bits. It goes back to 0. So that's counting away quite nicely. But what I want to do is actually light one light in turn. So I'll just change the sketch slightly to do that. Okay, so I've changed the sketch so that it outputs 1 and then 2 and then 4, 8. What would that be? 1, 2, 4, 8, 16 and 32. And then it actually outputs 64 and 128, which is why it goes blank for a couple of cycles, and slowed it down a little bit so it's easier to see. And that seems to be quite successfully putting lighting one LED at a time. However, what I want to do is see if I can do this with just 2 pins instead of 3. So my plan is to remove one of those clocks, or maybe link both clocks together or something, and see if it still works only on 2 pins. In fact, just to check that this is going to work and that I'm not doing some kind of trick, I made a kind of sliding backwards and forwards pattern just so I can check it. So now I'll try changing the code to only use 2 pins.